Welcome back everybody to another lecture in our series on physics. Today we're going to talk about chapter 21, artifacts. What is an artifact? You probably have seen them, probably haven't thought a whole lot about them, but now that we're going to talk about them, you're going to be seeing them all the time and you're going to have the tools to know how to fix them. An artifact is something that is not real in our picture, or it's something that's not seen in the image that should be. Maybe it's anatomy being displayed as the incorrect shape, size, position, or brightness. So an artifact is something in our image that does not accurately represent the anatomy that is being imaged. The four main causes of artifacts are violation of assumptions, which we're going to go over shortly, equipment malfunction or poor design, just the physics of ultrasound, or operator error. Now we're going to cover the violations of assumptions in pretty good depth here, but I do just kind of want to touch on those other three ideas of what causes an artifact. So equipment malfunction or poor design. When we are using our transducer, say we drop the transducer and we break some of those crystals on the front of the transducer. If those crystals aren't working, what we see from that, we learn in our transducer chapter, is that we'll get fallout in the picture. And where that fallout is, there should be anatomy. And if there isn't, then that's technically an artifact. So that's an artifact due to the equipment being broken or malfunctioning. Now there are also some physics of ultrasound, which kind of goes in with the violation of assumptions, but there's just certain things we can't break the rules of physics. Can't break the rules of ultrasound physics. It just is what it is, and we can't change it. So that can cause some artifacts in our images. And lastly, operator error. We talked about in our Doppler section about how it's very important that you as a sonographer know how to operate your tools. If you turn your color gain Doppler too low, then we're not showing the blood flow that should be in there. We're not showing the anatomy of the blood flow. We are introducing an error into our image because we don't know how to operate our machine. So the main causes of artifacts are going to be these violation of assumptions. There's 6 of them. Again, we'll talk about them shortly. But there are some other factors that you as a sonographer might introduce or broken equipment might introduce. So it's important that you understand ultrasound physics, and it's important that you know kind of how to troubleshoot your machine so you can rule out machine malfunctioning as a cause of artifact. Before we dive too much further into the idea of these artifacts and what they look like and why they're happening, one of the things that we just need to cover briefly, and this should be a review from ultrasound concepts class, are how to describe echoes that we see within the image. We call these image characteristics. The first one that we're going to talk about then is hyperechoic. Hyperechoic is a comparison word. We decide that a tissue is brighter or hyperechoic compared to surrounding tissue. So in this example behind here, we have this very bright area. Compare that to the tissue that's surrounding it. We have a hyperechoic area. Hyper means above the echo. Contrary to that, then we have hypoechoic. So this is when the tissue is coming back darker than what we expect, darker than the surrounding tissue. So again, hypoechoic is a comparison word. This tissue is hypoechoic to the surrounding tissue. It is darker or below echo. Lastly, then we have isoechoic as a comparison word. Isoechoic means equal brightness to the surrounding tissue. So you can see there's this very faint structure that is being measured in these images, but if you look at the echo texture, the echo brightness of this structure compared to the surrounding tissue, it's about the same. So iso means same echogenicity. Now the next 3 characteristics that we're going to talk about describe the structure in itself. So the first 3 are comparison. We compare the echoes to the surrounding tissue, or to what we expect the tissue to appear as. These next three are kind of independent. So the first one is anechoic. Anechoic means no echoes. And when it is anechoic, structures without echoes in them appear black on our machine. So commonly, anechoic things are going to be blood or fluid-filled areas like the bladder or the gallbladder or cysts within the body. So if you look in the image behind, we have this nice black area showing most likely, looks like maybe a cyst on an ovary. And so we have fluid within this black area. It is not creating any echoes to return to the machine. So the machine believes that there isn't anything there. Therefore, we get the anechoic appearance. Homogeneous, then, homo is similar or same. Geneous is creation. So we consider tissues that kind of look all the same, very smooth within. We consider those homogeneous. They have the same echo texture throughout. So we can see in this image of the liver here, the liver is very smooth. These echoes are all very similar to one another. They are just kind of running in with one another, very smooth. It's homogeneous. Heterogeneous then refers to having mixed echo characteristics throughout the tissue. So here we have in the background, I believe this is looking at a uterus, but we have some dark spots, we have some really bright spots, we have some mid-level grays, we have tons of different grays, and this is not the appropriate display of what this tissue should look like. Heterogeneous typically goes along with disease. We see as tissues change and react to pathology, we get more of a heterogeneous look to them. So again, heterogeneous, hetero means different, genius made of, so different mixture of echoes within a structure. So again, just to recap, I'm sure it is all review, but we had hypoechoic, hyperechoic, isoechoic, all comparison words. Is the tissue brighter, darker, or the same echogenicity as what we would expect or compared to the surrounding tissue? Anechoic, homogeneous, and heterogeneous all kind of describe the characteristics that are found within a structure. As promised, we were going to talk about those basic assumptions that are used in an imaging system. These 6 assumptions need to be known. So if that means memorizing them, please do. And you also need to understand what they are talking about. So our first assumption is that sound travels in a straight line. We know that sound has to travel in a straight line. We know that that's what it does. But the machine assumes that it never changes directions. It assumes that it goes straight up from the transducer and straight back into it. There's no change in direction of that sound. So number 1 assumption that the ultrasound makes is that sound travels in a straight line. The second one is that sound travels directly to a reflector and back. So this assumption assumes, again, that the sound leaves the transducer, strikes a reflector, returns directly back to the transducer. It doesn't bounce off in a different direction and then finally make it back. It doesn't curve, it doesn't do anything weird on its way back. So the number 2 assumption that the ultrasound machine is making is that sound is going to travel to that reflector and directly back. The third assumption is that sound is going to always be traveling at 1540 meters per second. Remember, we use propagation speed of soft tissue. It's kind of a general speed that the machine assumes. We know that that sound's going to be going through fat or through liver tissue or through blood or through lung tissue. That's going to change in reality how fast that blood flows. So the machine assumes always 1540 meters per second. We know that that's not always the case, and that is where some of our artifacts are going to come from. Number 4 is that reflections arise only from structures positioned in the beam's main axis. Now, if you recall back to an earlier chapter, we talked about grading lobes or side lobes, and we have that main beam axis, and then we have some sound energy that comes off to the side of it. Now the machine is really only listening from what it expects to be in that main beam. But we know if those side lobes or those grading lobes are strong enough, we can actually get echoes that return back to the transducer from those areas. And the machine doesn't know that those may or may not be there. It's assuming they're not. It's assuming all the reflections are coming back from the beam's main axis. Number 5 then is that the imaging plane is very thin. When we talked about elevational resolution, we discussed the idea that when you think about ultrasound, you think about these really, really thin slices, but there is actually some width to the beam. And because of that, then we get some extra information from above and below the area that we are intending to look at. And so the ultrasound machine assumes that we're not getting that, and if this assumption is broken, we'll see artifacts. The last one then is that the strength of the reflection is related to the characteristics of the tissue creating the reflection. In a nutshell, what that is meaning, and we'll talk about it a little bit more as we talk about the artifacts, is are the echoes that are returning to the machine for a certain piece of anatomy, are they what we expect them to be? Are they the correct brightness? Are they even visible? Are we getting the correct strength or amplitude of echo to reflect the tissue that it's imaging? Now, if any of these assumptions are broken, an artifact will be seen in our image. Most artifacts are going to be correctable by understanding which assumption was broken. Can we then change how we are using our tools to correct for that artifact? So as we study artifacts, I want you to pay attention to which assumption is violated. I want you to remember what that artifact looks like. How would you describe it in words? Can you recognize it in a picture? And then I also want you to know how we can correct it. Our first artifact that we'll talk about then is reverberation. Reverberation, when you see it in your images, it's going to appear as multiple, equally spaced echoes. Let me say that again. Multiple, equally spaced echoes. These are going to appear as parallel lines as they go down into the depth of your picture. Typically, the first 2 reflectors are going to be your real reflectors. After that, it's all artifact. As we look at the artifact, we're going to see that the echoes are going to decrease in brightness with depth of the picture. And a lot of people kind of think this looks like a ladder. Let's take a look at these pictures here. We have a very bright reflector here. This is actually a needle within the tissue, most likely creating a sample. And what is happening is sound is coming down from the transducer, is interacting with the needle, and it's actually interacting within the inside of the needle. It is hitting both of the walls, both of the strong reflecting walls of the needle. So what happens is that sound energy kind of just keeps bouncing back and forth through that needle. And as time goes on, as that sound bounces back and forth through there, a little bit gets sent back to the transducer. Milliseconds later, a little bit more gets sent back, a little bit more gets sent back, and that keeps happening. And so the machine thinks, well, this echo took a little longer to get here, so let's place that here. Well, this next echo took a little bit longer, so that must be a little bit deeper, and so forth. So the machine is assuming that these echoes that are coming back came straight from a reflector and returned back to the transducer. But in reality, the sound has just been bouncing back and forth in this area. Time has gone by, so now we're introducing that time of flight rule, and the machine is calculating deeper and deeper and deeper reflections. So we get equally spaced parallel lines that go deep into our picture. They lose echogenicity because of attenuation as we get deeper. Here again is another very bright reflector. And what we're seeing again is the sound is bouncing back and forth between these reflectors, getting to the transducer a little bit later each time. The machine thinks, oh, that must be a little bit deeper, using my 13 microsecond rule, and it displays parallel lines deep into the picture with decreasing echogenicity. Here again is another example. In the heart, we have a mechanical mitral valve. The mitral valve is a artificial substance which does not interact with ultrasound as well as soft tissue does. We get some bouncing back and forth of the sound, and then we start to see those equally spaced ladder-like reflections into the body. Now the biggest way that you're going to fix reverberation is really just coming at the area in another window. Sometimes it's going to be unavoidable, especially with like our needle procedures. The needle just really interacts with the sound differently than soft tissue does, just like the mechanical valve. Those kind of artificial, not natural structures that are within the body can quite often cause these reverberations. The biggest problem is that we're having that 90 degree, that normal incidence, and so there's a lot of opportunity for sound to bounce through here. Say we came off a little bit from the side and shot through this area this way, we most likely would not get the same interaction of sound, and then we could see this area posterior to the needle. Sometimes it's not a big deal that that reverberation is in there, or any artifact is in there really. If we know what was back there, we saw it, maybe our bigger concern is where's that needle going. Maybe we're not then as concerned about correcting for that reverberation. So again, reverberation is going to be equally spaced echoes that appear deeper into the image with decreasing echogenicity. And this is breaking assumption number 2, that sound traveled directly to the reflector and back. So I just want to draw this out one more time for you. Reverberation is one of those artifacts that we're going to see quite often. So here's our transducer. Here is our really strong reflector. There's usually a couple of them really close to each other, so let's pretend like we're using a needle in the body. So that first sound is going to come back, strike the needle, and it's going to send an echo back. And so our picture puts a bright line there. Remember, some of that sound is going to keep going forward, and what's going to happen is it's going to hit that other wall behind it, and then that sound is going to get sent back. So now we get that second reflector. So our first 2 reflectors are usually usually true reflectors. But what happens is sound is going to get trapped in between here. And so what's going to happen is that as time goes on, more sound is going to come back, and the machine is going to put a line there. A little bit later, another reflector that's bouncing, then there comes back, the machine puts it in. And that's going to keep happening, causing our artifact to be displayed. And remember, as we go deeper into the picture, these deeper lines are going to become a little bit less echogenic because of attenuation. The next artifact then is comet tail artifact. This is actually very similar to reverberation. And with comet tail artifact, also known as ring down artifact, what we see are typically single hyperechoic lines that extend off of a certain area of anatomy. So again, assumption number 2 is broken in this one, in that the machine expects that these echoes are coming straight back from a reflector. But in reality, what is happening is that sound is bouncing between 2 very small and very close reflectors. So in reverberation, we have a little bit bigger, strong reflectors. In comet tail artifact, we have very small, very close together reflectors. And so what we see then is that we see kind of this ladder appearance, but now that space in between has kind of been squeezed out. So reverberation and comet tail artifact are very similar to one another in how they are created, except comet tail artifact squeezes those spaces out. The latter is not quite as prominent. So it almost looks like just a bright white line extending. Now we're going to see these comet tail artifacts quite often in the setting of air. So that might be air in the lungs, as we're seeing in this picture here. Or in this picture here, we have air in the lungs around the heart. This example here is showing air in the biliary tree. So we're getting these little comet tail artifacts because of the air that's within the liver. This example here is air within a needle. So we're seeing that comet tail artifact come down. And then this one actually is of the gallbladder. And this one is actually showing adenomyomatosis. So sometimes these comet tail artifacts can help us to diagnose diseases or pathology. Adenomyomatosis are a bunch of tiny little crystals that sit within the gallbladder wall, and they cause a different type of ringing with the sound beam. They cause the sound beam to kind of bounce around within the tiny little crystal of cholesterol, creating that comet tail artifact. In the case of the liver here, air within the biliary tree is called pneumobilia. And so that helps us to show the radiologist there's pathology going on here. So sometimes when we have artifacts, we don't want to correct for it because it's actually helping our diagnosis. So heading back to the whiteboard here, we have the transducer again. And I said that we typically see comet tail behind air. And that is because we have these little air bubbles next to one another. And as that sound comes through here, there's this kind of cone shape that sits in between that air bubble. And the way we have this kind of conus area in between gas bubbles, the sound bounces back and forth in here in a different manner than it interacts with soft tissue. And because of that, then we're getting some bouncing, sound goes back, bouncing, sound goes back. But this happens so quickly because these tiny little air gas bubbles are really, really close to one another. So what we end up getting is the machine putting lots of little echoes right next to each other, and we get these really bright hyperechoic lines that extend off the area. So this is why sound interacts with air kind of in an odd way, showing those artifacts, because we kind of get this conus area in between. Now in the case of adenomyomatosis, I talked about that there's this crystal in the gallbladder wall. So we have this tiny little reflector in here, and as the sound interacts with this tiny little crystal, it's going to make this crystal ring weird, and it's going to cause little reflections to come out of it, again making those little reflections come off the edge of it. So reverberation, equally spaced lines going deep into our picture. Comet tail, same concept. They're just really, really, really close together and usually very compact, so we get kind of this more solid appearing line. As far as correcting comet tail artifact, again, maybe we don't want to. Maybe it's helping us to diagnose the patient. Otherwise, usually changing a window is going to be your main way of avoiding that ring down artifact, just because of how the sound is going to interact differently with the sound bubbles or with the crystals. Our third artifact then is shadow. Shadowing is considered an artifact because of rule number 6 being broken. Rule number 6 says that the strength of the reflection is related to the characteristics of the tissue creating the reflection. So what we are seeing with shadowing is an area that is hypoechoic to possibly anechoic in a region. We typically see it behind an area that is highly attenuating, like bone, gallstones, plaque within the arteries. What ends up happening then is that all of the sound is reflected at that interface, and because of that, there isn't enough sound energy to make any anatomy behind the reflecting structure. So let's take a look at some of our examples here. This is the aortic arch. We have a little bit of plaque in here. The sound is coming down. Basically, all of it is being reflected back, and because of that, we don't have any sound energy behind it to display the anatomy. Now this is artifact because there isn't just this giant gaping hole in the patient's anatomy. There is tissue back there, but it's artifact because we are not getting the correct reflection or strength of reflection from an area. We should see echoes through this area, but we don't because there isn't enough sound energy to create any. In this example on the top here, we have a bunch of gallstones. Again, the gallstones are reflecting all of that sound back. Behind it then we are just seeing kind of this void of anatomy. There's actually should be more kidney displayed back here. There should be more liver displayed back here, more soft tissue. Again, this is artifact because we are not seeing the true anatomy. Same in this fetal face. We are looking at some bones in the face, the maxilla and the mandible are creating shadows, thus leaving kind of this empty space behind. We know that there's a neck. We know that there's more skin back here, a spinal column, but because of the way sound is interacting with these highly attenuating structures, we are not getting that true anatomy. So how do we fix it? Sometimes we leave it. It is what it is, especially with gallstones. Seeing shadows behind gallstones helps us to identify that these are in fact gallstones. Seeing plaque with shadowing behind it tells us that's calcified plaque. That helps us to create more of a story for the patient's pathology. So sometimes we leave it. Other ways we can fix it is use our TGCs. Can we increase in this one area, can we use our TGCs to kind of help for all the attenuation that occurred? Or do we want to try imaging around it? If I come off to the side here and try to shoot my sound beams underneath where that plaque is from a different angle, I'll get some more information back here because they're not interacting with the plaque in the same way. Maybe we want to try a new window, try a new angle on the area, showing in different pictures that that anatomy truly is there and appears normal. So in the event that we have shadowing in our images, definitely show the shadow, especially if it supports a diagnosis. But then you also want to make sure to try new windows so you are truly seeing the anatomy that should have been displayed below the shadow. A similar artifact to shadow is edge shadow. And again, we're breaking assumption number 6 that the strength of the reflection is related to the characteristics of the tissue creating the reflection. And what happens with edge shadow is typically we'll see some sort of rounded structure. So here we're seeing the gallbladder in transverse. It's this round structure here. Here we are seeing a fetal head. We can see the skull in that round ovoid structure. With edge shadow, what we see then is that right off the corners or edges of the circle, we get these lines that are hypoechoic, therefore not displaying the correct gray that we would expect for this area. So we can see these hypoechoic lines coming through the liver. We should expect the same level of gray through this area, but this is artifact because it's not showing the anatomy as it truly is. Same idea with the fetal head here. We are getting sound that's interacting with the edge of the circular structure. It is causing the sound energy not to continue, so we are missing that information through the shadowing. Now the way that physics works with this round structure is the sound beam is coming through straight from the transducer. It interacts with the edge of the rounded structure, and as it interacts with the edge, the sound beam is diverted in another direction. So the sound energy that should have covered this area actually got sent off in another direction, and it never made it back to the transducer. So the machine assumes there is going to be nothing there. It starts to lose its intensity because it's being sent in another direction. So we have our round structure again, our transducer is up here. The sound is coming down, interacting with this edge, and instead of continuing, sending some image back and then continuing forward, the continuing portion of that got sent off in another direction. So we're left with an area that never receives sound energy or receives very little sound energy. Same thing on this side, sound is coming down, interacts, so it sends some reflections back so we know where that edge of that rounded structure is, but instead of some of that continuing straight forward, we get divergence and the sound goes in another direction. So edge shadow is due to the way sound interacts with that curved edge. For correcting for this, again, it's going to be using TGCs to kind of lighten that area, see if we can get it to match up with the area around it. To change the path that we're using, to change our window, our angle, as we are imaging near that rounded structure. Enhancement then is kind of just the opposite of shadowing. So we have a structure that is very low attenuating, and because of that, all that sound energy just keep moving through. Stronger sound energy typically creates stronger reflections, and so we see a brightness that shouldn't be there. So again, number 6 is being broken when we are talking about enhancement, because the strength of the reflection related to the characteristics of the tissue is not what is being shown. Typically this is going to happen behind fluid-filled structures, maybe the bladder, maybe the gallbladder, a cyst somewhere within the body. So we see these anechoic fluid-filled structures. The sound comes in, doesn't really attenuate at all through here, so we still have very strong sound information that is continuing through. And because of that, then the echoes that return from that strong sound energy are going to be brighter, they're going to be stronger. Now if we look next to it, we would expect that this bright hyperechoic area should have been actually the color of this gray color next to it. So this is artifact because we are not seeing the anatomy the way we would expect. Same idea over on this side, we have liver tissue, kind of this low level gray. We have a cyst within the liver, not attenuating the sound. And because of that, then that liver tissue behind the cyst looks very bright, hyperechoic. This is not the right presentation of this tissue back here, therefore it is an artifact. So same idea as shadowing, we want to make sure that we are using our TGCs, maybe darken this down a little bit just so everything matches up, looks a little bit nicer to the eye. Maybe we'll leave it. Having a cyst showing that posterior enhancement is actually very important to say, yep, that's probably a cyst. Otherwise, we can always try different angles so we don't interact the same way with that structure. Focal enhancement is, again, breaking rule number 6, that the strength of the reflection is related to the characteristics. And that's because with focal enhancement, what we tend to see is a bright band that goes side to side at the level of our focal zone or our focal point. So in this image here, we can see this brightness that comes across side to side, and it is at the level of our focus here, those two little yellow hourglasses. What happens, if you recall, when sound energy is concentrated at the focus, it's actually very strong through here. So again, we have strong sound energy. Stronger sound energy is going to create stronger reflectors. That's why these are going to look a little bit brighter. So to correct for this, we are going to want to use our TGCs. We're just going to bump them over a little bit just to compensate for that strength at the focal zone, just to kind of make it even on either side of it. The other thing that you can try doing is changing where your focal zone is, especially if, say we have this gallbladder here, And we want our gallbladder to be anechoic. Echoes within the gallbladder actually make us think there might be some pathology in there. So if TGCs aren't quite working, I could lower my focus. Therefore, that banding would be out of the structure that I'm mostly interested in. We can see the same thing on here. We've got our focal zone, and we can see that banding, that side to side enhancement or brightness through the picture. Because the echoes are not what we would expect them to be, because they are abnormally bright, that is considered an artifact. Our next artifact is mirror image. And mirror image can occur both in B mode, in color mode, and in Doppler mode. Mirror image artifact is breaking two assumptions. The first one being that sound is traveling in a straight line, and secondly, that sound travels directly to a reflector and back. When we have a very strong reflector, keyword strong reflector here, so a very strong reflector internally in the body, it creates almost, well, basically like a mirror within the body to reflect that sound over. When we are looking at a mirrored artifact, the anatomy that is closest to the transducer is the real anatomy. The anatomy deep to the reflector is the false anatomy. This is the artifact down here. We have a liver here. We have our strong reflector of the diaphragm. And then we have our artifact behind it. In B mode and in color imaging, what we typically see is that mirror image is being displayed on an area that tends to be a little gassy. So this is over lung. This is over lung. This one is over lung. We can sometimes also see it in the abdomen using the gas of the bowel if there's a strong reflector down there. Now what's happening with mirror image is sound is coming out of the transducer and it's interacting with this strong reflector. Now the strong reflector has sent so much sound energy back that sound energy coming back also is interacting with the tissue that it's going through. And because of that, the sound strikes this and then gets sent deep into the body again. And when that happens, these reflectors are going to come back to the machine a little bit later. And as they come back to the machine later, the machine calculates them to be deep into the body. So let me just go over that again so we can explain it. Again, we have our transducer up here. Let's just say we have some pathology in here, and then we have something that's a really strong reflector. My first sound is going to come back, or goes in, interacts with my pathology, and that's going to be displayed on my image. Remember, some of that sound is going to continue through, and that extra sound that continues through then also interacts with my strong reflector. So now my strong reflector gets displayed on my image, because that's going to head back. But then what else happens is this strong reflector is sending strong echoes back, and that is also going to interact with my pathology or with my anatomy that's in the area. So as the sound interacts with this as well, the machine is going to get these echoes back as well and think that they are coming back a little bit later. Remember, the machine is calculating this first pink one. The machine's thinking that this is the original, and so any sound that's coming back right now is from this original sound beam. But because the sound is interacting with the reflectors again later than what the pink one should be, the machine is calculating that out, thinks they are going to be further away and deeper into the body. So with mirror images, we get exact replicas of the anatomy across the strong reflector. So again, we have probably maybe an amoebic abscess here in the liver. We can see it again reflected across the diaphragm, that strong reflector. Here we are in the heart. We can see the heart structures. We can see that mirroring across. We're getting exact replicas. With our color image, we have a vessel here. The vessel wall is a very strong reflector. And so we get a duplicated exact image, exact replication of the vessel deep into the body, kind of displayed on the lung. This is most likely subclavian artery. So it is not uncommon with strong reflectors that we see that mirror imaging. Now we also see this in the idea of Doppler. We talked about this in the Doppler chapter, but we call it crosstalk at the time. And what is happening, it's getting reflected. It's the exact replica of the waveform being displayed across the baseline. And that's because Doppler can't tell which direction things are going or coming from. And it's kind of the same idea for our color and our beam mode. The transducer thinks it's coming from the main beam, the original sound that was sent out, but in reality, we're getting some duplicate reflections from the return echoes. So how do we correct for mirror image? We can decrease the gain of the picture. That's just going to kind of eliminate or decrease the strength of the reflectors that we're seeing in that reflection. We can decrease the power. So if we decrease the energy that's coming out of the transducer, it will not interact with that strong reflector the same way. Or we can change the angle that we are incidentating at. Again, we're changing how the sound interacts with that strong reflector. We won't get the same interaction if it doesn't hit it at a different angle. Speed error brings in the idea that sound always is traveling at 1540 meters per second. We know that's not true, and sometimes it shows up as an artifact in our pictures. So sound is leaving the transducer at this point here. Again, we're looking at the liver here, and the liver we know has a different propagation speed than 1540 meters per second. And so as the sound interacts with this faster propagation speed, it strikes a reflector and sends it back. Well, because the sound was able to travel through here faster, the machine thinks that it came back sooner, and therefore those echoes are going to be displayed earlier. So in speed error artifact, we tend to get kind of like a broken step off of the anatomy. Now, speed error artifact is also known as range error artifact, and that is because the range equation is not using that 1540 meters per second, or excuse me, it is using the 1540 meters per second, but the sound isn't always traveling at that speed. So let's look at this example here. We have sound again coming in from the transducer, expecting all these echoes are coming back at that 1540 meters per second. It then interacts with a structure that has slower propagation speed. And so the echoes that are coming back from here and beyond are also going to come back a little bit later. So the machine misregisters where they think those echoes are coming back from. So we can see here we have this broken diaphragm. There's a step off. This chunk of diaphragm sits lower than where it actually should be. So that is the artifact. We are not displaying the anatomy as it actually appears. So let's look at our example here again, just to reiterate. So here's our transducer. Let's say we have a structure here and a structure here. And let's say, our average is 1540 meters per second. Let's say that this first structure here has a propagation speed of 1380, and we'll say that this other one has a propagation speed of 1620. So this first structure has a propagation speed that is slower than what the machine is assuming, and our second structure has a propagation speed that is faster than what the machine is expecting. And then let's say this is all in the liver and we have some diaphragm behind it. Okay, so this is the real anatomy. This is what is actually happening in the body. So our first sound beam comes down, interacts with this slower structure, and now anything past this will also be a little bit slower. So these echoes are going to return slower than the 1540 meters per second. So when we have a longer time of flight, the machine assumes that that is a deeper structure. So on our picture, we'll see something like this. We'll see a deep section that's kind of broken off on from the structure because of that long time of flight. Let's compare that then to the other structure, the one that has a faster propagation speed. Sound comes through, travels very fast through here, and keeps traveling through, and we're getting our reflectors back from all of these areas. Now, because sound is able to travel faster through that area, the machine thinks the time of flight was short. Therefore, this must be a shallow structure. So it's going to produce something that looks like this. So when our structures have slower propagation speeds, the time of flight increases, and what we see is deeper reflections. Compared to structures that have faster propagation speeds, the time of flight is shorter. The machine calculates it to be more shallow. Correcting this then would require us just to use a different angle so our sound is not interacting with those structures that have the different propagation speeds in the same way. And we definitely want to take a look from different angles, make sure that the anatomy that we're seeing is actually all connected. Sometimes you'll see it in like fetal bones. Fetal bones can actually break in utero. If we were to see kind of this range error artifact and it looked like the bone was broken, we'd actually really want to make sure that we insonate from a different angle, not interact with tissue the same way, so we can make sure that that bone truly is broken versus it just being artifact. All right, our next artifact then is lobes. And lobes are breaking the assumption that reflections arise only from structures positioned in the main beam's axis. So we talked about this earlier. We talked about how our main beam has all that strong sound energy, and when we're using array transducers, we can get grating lobes off the side of it. Well, when we have those grating lobes, they actually are strong enough to create reflections that are going to head back to the transducer. And so when that happens, the transducer and the machine expect that those reflections came from the main axis. So the transducer is like, cool, let's display those. And then they end up in our picture as artifacts. So here we have, and they're typically best seen in areas that are anechoic, because we expect this bladder, these dark areas, we expect them to be anechoic. But because of the lobe artifact, we can now see structures are being displayed within. And the reason that it's more prominent on anechoic structures is just because this bright reflector will just kind of get overlaid in the rest of the tissue. So they just seem to be more prominent. Oh, jumped ahead here. They just seem to be a little bit more prominent on our anechoic structures. So again, we have our transducer. I'm just going to draw something that we would expect to be anechoic in here. And we have our main beam coming down. And we're typically using array transducer, so we have these grating lobes that also have sound energy. And usually we have some soft tissue out here, right? It's not just one random floating structure. And so what we're going to get is we're going to get reflections back from the main beam as it interacts with anatomy, but we're also going to get reflections back from these grating lobes. And so then what ends up happening is we see the picture that we got from the main lobe, but then we also start to see a little bit of information that we got from those side lobes. And because the beam thinks, or the machine thinks that these echoes were coming from this main beam, they get kind of superimposed into our main beam's picture. So lobes degrade our lateral resolution. They typically are going to be low-level echoes. Sometimes they are exact replicas of information that's off to the side. This is why we use harmonics, because remember, harmonics aren't strong enough to create gradient lobes, so that's a big way that we can fix for side lobes. We can also use those tricks that we learned, apodization, where we increase the strength of the beam in the center, or subdicing of the transducer elements. Refraction describes how sound interacts with structures, therefore creating replicas of the anatomy. So with refraction, sound comes in from the transducer. It then interacts with a little bit of tissue that refracts the sound beam into another direction. And the machine thinks that that refracted information is coming from the main scan line that was originally sent out, but because it is not, it gets displayed as a second area. So you can see in our examples here, we have the sound beam coming down. It interacts with the refracting generating medium. The sound then, some of it keeps traveling forward out of the true beam and some of it gets refracted. That refracted sound interacts with the real tissue, and because the beam or the machine thinks that that reflection is coming from the original source, we also get an artifact displayed. So with refraction, what we see is a replica of the anatomy in the side-to-side view. So mirror image was exact replica, but deep to shallow. Refraction is an exact replica, but side to side. Over in our example here, we have, again, the sound is coming in, interacts with the refracting medium. Some of that sound images the real anatomy. The machine thinks that it all came from the intended source, and then also displays that second portion. So let's take a look at the whiteboard again here. So we have our transducer. This will be our refracting medium. In the abdomen, it tends to be the rectus abdominis muscle. And so quite often we'll see reflection or refraction of the aorta. So what happens is the sound beam, say the sound beam is angling this way. And so it is steered to get the information that's over here. As that sound beam interacts with the muscle or whatever is going to cause the refraction, some of the sound keeps going, some of it gets refracted. Now the machine doesn't know that the sound changed direction. It thinks all the information is coming back from the blue echoes. So those echoes will also return. But what happens is that this sound is going to interact with the aorta and return echoes back to the transducer as well. Now again, the machine thinks everything is coming back from that blue area, but in fact we got some pink reflections back, and the machine will calculate that then as information from the blue area. So we get side-by-side replication of anatomy due to a change in how the sound has been traveling. So with that then, refraction breaks rule number 1, that sound travels in a straight line. Sound took a turn or refracted with that muscle, sending back information from a different area within the body. Now again, to correct for this, we are going to try imaging from a new window, or we are going to try to angle the beam in a different way so it doesn't interact with the refracting medium in the same way. Slice thickness we have talked about before, and is the same as our elevational resolution. So this is breaking assumption number 5, that the imaging plane is very thin. Slice thickness artifact is also known as section thickness artifact or partial volume artifact. And again, this is typically mostly seen, or a little bit more obvious, in areas that we expect to be anechoic, but we're getting kind of some low-level echoes within it. So again, we can see the heart here. We expect these chambers and vessels to be anechoic, but we can kind of see that there's some kind of just low-level shadowing that's coming through here. Same with this urinary bladder, we expect it to be anechoic, but now we can see that there are some little artifacty shadows or echogenicities that are coming through here. So these are the slice thickness artifact. What we are catching is something that sits within the width of the beam and then being displayed within our picture. So the machine is assuming that the imaging plane is very thin. Everything that we are getting in our picture is what we want, is coming from a very thin source, but in reality we are actually catching just some extra information outside of what we are visualizing. So in the case of the heart, a little of the beam might be interacting with some lung, and so we are getting just kind of like this fuzziness from the lung over a picture. In this bladder picture, we're probably catching a little bit of the bowel, and so we're seeing just some reflections being displayed in our picture that actually are of bowel. So to correct for this, we can use TGCs to kind of eliminate the strength of those extra echoes. We can try using harmonics, or we can use our 1.5D array transducers. Now the next couple of resolution artifacts I will talk about, we've already discussed in detail, so I'm not going to spend a whole lot of time on them. I also want to point out that they don't really break any assumptions per se. The closest one that they technically break is that the beam is thin. And we know that the beam has width in all 3 directions, and depending on that width, we know how it'll interact with different structures. So lateral resolution artifact is also known as point spread artifact. Again, we will only see 2 structures being independently displayed as long as the beam cannot interact with both of them at the same time. So we have the beam coming out, it's hitting both of these structures at the same time. The machine doesn't know that they're 2 separate structures, it displays it as one. In this example here, the beam is not striking both structures, so it recognizes that there is indeed only one structure. Again, as we get deeper into our field, the beam diverges, interacts with 2 structures, it can't tell that they're different, and so it creates a display as one. So lateral resolution completely depends on how far apart 2 reflectors are. To fix for this, we can adjust where that focal zone is, where that narrow portion is, and attempt to get more detail by adjusting the beam to make it thinner. Axial resolution, we've also talked about. Again, the closest assumption is probably number 5, but it's not truly what's happening in this case. What ends up happening is that our wavelengths are longer or shorter than how far reflectors are apart, and this is going to determine how these reflectors are displayed. If two reflectors are too close to one another, that one wavelength interacts with both structures, then they are going to be displayed as one structure. Multipath artifact is kind of a combination of mirror artifact and I guess probably lobe artifact in a way. What ends up happening though is that sound travels into the body and it bounces off of strong reflectors, but it doesn't bounce in a way that we would expect. So the sound comes in, it might bounce off of this bladder wall and then bounce off of this bladder wall, maybe up here again, and then finally make it back to the bladder. And because it's kind of taking some detours through here, what we end up getting is a reflection across a strong reflector, but it is not an exact replica. So that's the big difference. Mirror is exact, multipath is kind of a weird mix of what we just saw. So we can see here we have the bladder, but we can see that it's not an exact replica of that bladder reflector. So this is an artifact out here. And it's because the sound interacted with strong reflectors of the bladder wall, but went a couple different directions before heading back to the transducer. So we can take a look at that again. We have our transducer, we have our structure here. And as the sound comes in, it interacted with this wall first maybe, bounced back, but some of it got sent off in another direction, and then that will eventually head back. And maybe some of it bounced off in another direction, and that will eventually head back. So the machine thinks, again, as all these random path echoes are coming back, that they all came from this original one, and so the machine will then display something kind of deep to the original structure. So this is deep to the true anatomy, but it is not an exact replica. To correct for multipath artifact, we're just going to change the angle as to which we're incidentating so we don't get the same interaction with the strong reflectors. Curved and oblique reflectors also have a hard time sending back true anatomical representation of the echoes that create them. So kind of like with edge shadowing, the sound gets sent in different directions. It's kind of the same idea with these curved and oblique reflectors. We can see in our picture here that the SMA, so this is the aorta here, the SMA is a blood vessel that comes off of the anterior part of it, and it actually kind of curves up and around and then travels parallel with the aorta. And so you can see the wall really well here, you can see the wall pretty well here, but we're actually missing some information in here, and that is because this is a curved or oblique reflector. So let's go back to the whiteboard so we can kind of show what's happening here. We have our transducer and we have this kind of curved area. We'll just draw something like that. We know that when sound interacts with at 90 degrees to a structure, we get a really nice solid line there. But as that sound interacts with curved, what ends up happening is some will come back, but some kind of get sent off in another direction. Anything curved is going to send our sound in another way. So that area might just be kind of loosely reflected compared to the normal incidence area. So we just don't get the same amount of information coming back from those curved reflectors. And then again, the sound could make a strong interaction with that 90-degree reflection again. So technically with curved and oblique reflectors, sound is no longer traveling in that straight line because it's being refracted into another area, and that sound is not necessarily traveling directly from a reflector and back. Typically, to correct for curved and oblique reflectors, we just want to come at them from a different angle so we can see that there truly is a nice wall coming in through here. If we could kind of come in from this angle a little bit more, we would see, if we could come in from this angle a little bit more, we would see that wall connect through. Temporal resolution artifact. then is something that we've talked about in great detail already, but we talked about how if our machine cannot refresh the picture quickly enough, we start to see kind of some jumpiness in our images and our real-time imaging. So temporal resolution artifact occurs when the frame rate or temporal resolution is too low to depict motion of anatomy accurately. Spatial resolution artifact refers to the idea that we want to see detail within our picture. So spatial resolution artifact can change as we change line density. If we have lots of lines, we're going to have a lot of detail that improves the picture that we're getting. If we have low line density, we are going to lose detail, and because we're losing detail, we are actually introducing artifact. We are not displaying the anatomy as it's intended. Axial and lateral resolution can affect our spatial resolution. If there should be two structures and there's only one, we're not showing the anatomy that is truly there. So we're not seeing the true anatomy. That's an artifact. Horizontal scan lines in the display, and that depends on how our monitors are created. If our monitors don't have the resolution to display all the true anatomy, that can introduce spatial artifact. And pixel density. We know that the more pixels there are, the more detail that we can get. So if we have a low pixel density, we are not, again, displaying the anatomy in its true form. So spatial resolution refers to the detail. Spatial resolution artifact refers to not having enough detail to show true anatomy. Another artifact that we come across that is probably not super common in B mode is range ambiguity artifact. Now we talked about range ambiguity with continuous wave Doppler, and that we don't really know where those Doppler echoes are coming from. We can't choose where we are picking to get the Doppler information. Range ambiguity artifact is going to happen in B mode, and it's going to happen in that some echoes are going to return to the transducer later than expected and then be displayed. So let's go to, so we have our transducer. Let's say this is our field of depth, and we have a couple of reflectors in here. Sound's going to interact with those, travel back, and we get our picture, right? Everything's fine. What if there was a reflector that was beyond our field of depth? And we know that sound is going to keep going. Well, technically that sound is probably going to attenuate, and as the next image is created, might not even interact with it all that much. But what if we had a really, really strong reflector down here? So that sound kept traveling, and now those echoes are coming back while the next picture is being created. That really strong reflector is going to show up in our picture. And it's going to show up in a random spot because the machine thinks that it came back from the current picture that's being made. So range ambiguity artifact is kind of similar to aliasing in that this deep reflector is being displayed in the wrong spot, and it's because the machine didn't realize that that was from a previous echo or previous pulse that had already been sent out. So we're getting kind of a latent echo from a previous pulse being displayed in our picture. Now this might happen quite often, more than we really realize, and we just don't pick it up because the reflections are so nondescript that they probably just look like noise within our pictures. So the only way to really improve this or decrease the chance of this happening is just to increase our field of depth. That way we can actually see those reflectors, and the machine is going to get them back from the time that we expect. So the last couple concepts that we're going, or most main concept that we're going to talk about, is the idea of noise. And noise, we've talked about it before, it's something that's just in our pictures. There's just interference of sound interacting with the earth, with our machines, with the body. There's just extra information that's going to occur. And so noise artifact is really just thought of as kind of normal interference that's always going to be in our picture. It doesn't have any relation to true anatomy, that's why it's artifact. But again, it's just something that we expect, it's something that occurs in our pictures. We can correct for it with using harmonics or changing the strength of our signal to noise ratio. We can kind of work around it. So noise is an artifact, but just something that we expect to be there. Speckle is another type of artifact that occurs, and speckle is going to occur more at the top of the ultrasound image. And at the top of the ultrasound image, if you've ever noticed, you have kind of these dark lines or bright white lines that don't really show anatomy. Let's see if I can get back to a picture here. Here we go. So this is speckle up at the top here. We have skin line, probably some other tissue interfaces here, but they're just not really displaying any true anatomy. We always kind of have these lines through here. This is where the speckle typically occurs. And speckle is just the sound wave interacting with one another. The wavelets are kind of deconstructing one another, and therefore we just don't get true anatomy. There really is a skin line. There really is, the next epidermal line, then the fat line, maybe a fascial plane in there. And technically, if we had beautiful transducers that didn't cause that speckle to occur, maybe we'd actually be able to see it, but we don't. So we get artifact because we are not showing the true anatomy in that very, very, very near field. Lastly, some other sources of noise that may occur in our pictures are maybe some outside interference. So we can get electronic interference, we can get talking can cause some issues with our pictures, biological interference, bowel moving or kind of growling, it makes noise, or other machines, surgery, that kind of stuff can introduce noise into our picture. Just as a couple of examples of noise that I have experienced, when I went up to the ICU to scan a patient, some of the machinery in the ICU just is at the same wavelength and interacts very oddly with our transducer, with our machine. And so you can see these extra reflectors that don't belong there. And it only happened with this one transducer, so if we changed transducers, we got rid of those extra external noise sources. Another place that I worked at, every time the handicapped door opener was used, it for some reason was in the same wire setup as the machine was plugged into, and so that electronic interference would show up in our pictures. So because it was not true anatomy, it is considered an artifact. So just be aware that there are external sources of artifacts as well, and sometimes you have to change transducers, turn other machinery off, or have the patient ask them to stop talking, because that can interrupt some of our information as well. And that is the end of artifacts. So now that you know what these artifacts look like, you should be able to look at a picture of an artifact and be like, that's comet tail, that's mirror, that's reverberation. You should be able to identify what they look like by seeing them. I also want you to be able to describe each artifact. What does reverberation artifact look like? What does shadowing look like? What does enhancement look like? You should be able to use words to describe those artifacts. Secondly, then, I want you to have a loose idea as to what is happening with that artifact. Is it a matter of the wrong brightness being displayed? Is it a matter of the echoes came back late? Is it a matter of the echoes bounced around in the body before returning? What happened? What rule, what assumption was broken that caused that artifact to be made? So my best suggestion to you, work through your workbook and then also create a chart. Map out this information in a way that you can kind of see it all at once. Draw pictures of it. I think that's going to be very helpful as well. And use that as a good study tool to just kind of lay it all out, see it all at once, so you can recognize similarities and differences between the artifacts and what they look like.